Flutube. Get it straight.
Okay, now let's look at the same problem from another perspective. Let's look at the stream function for this, and let's just stick to the first quadrant for this one. So remember, the stream function is this psi term, and it's defined in a way that its derivative with respect to y is equal to the velocity in the x direction, and its negative derivative with respect to x is equal to the velocity in the y direction. So we know u is equal to ax, that was given, and that's equal to dy, to d psi dy by definition. So we can separate this and integrate, and we're doing an indefinite integral, so we need a constant of integration. And here we have to do some formalities here. They'll work themselves out, as you can see, but we get the integral, we get a times x times y, and we should really call this constant of integration f1 of x, because it could be a function of x, because we're taking the integral with respect to y. So if we took the derivative with respect to y of f of x, we would get a 0, just like as if it was a constant. So generally speaking, it could be f of x. So psi is equal to axy times f1 of x. Now if we do the same thing with v and the negative d psi dx, in this case, which we know is given as a negative ay, we get pretty much a similar sort of thing. We've got another function. In this case, it could be a function of y, right? Because if we took the derivative of this with respect to x, we would get 0, just as if it was our constant. So in all, we have the psi is a combination of these two things. Since we got the same function up front for both of them, we can just use one of them to cover both of our cases where we did the v and the u. So we've got that function here, but then we've got both of these potential constants. Now then we kind of work it out that they must be equal just a constant. They can't be a function of x and y, because then it wouldn't work out when we took the derivative with respect to y. We'd have this problem over here going to 0, and we wouldn't get the u. We get a derivative with respect to x. We wouldn't get just the v. So we can just put it in as an arbitrary constant. So it's kind of a much to do about nothing there. But we ended up with this a times x times y is equal to a constant. So we know a is equal to 0.3 in this problem. It was given. So we have 0.3 xy. Okay, so that's this general stream function. So we need to get specific if we're going to draw them. So let's pick an easy one to start out with. Let's say that c can equal anything. So let's say it equals 0. And then we can call this stream function number 1 here. And then we can notice that if x equals 0, then y could be any number. If y equals 0, then x could equal any number. So this would be basically the y-axis and the x-axis. So these are actually part of the stream function. Otherwise, that's sort of the easy, trivial one to get. The harder ones to get are just to pick some convenient numbers, where we say, okay, let's let the stream function of for 2 equal to 0.3, and then that would mean that x times y is equal to 1. So we chose that basically because we had this constant 0.3 in front of it. So if we choose multiples of that, say we choose 2 times 0.3, we can say psi 3 is equal to 0.6, then xy is equal to 2, or y equals 2 over x, and so on. So we have these hyperbola-like functions that we can plot up, and we can see them. Here's the one that we did at first for psi 1, which is just the axis here. And here. And then we have psi 2 psi3, psi4, and so on. So these are all headed down this way. So I've superimposed the A, B, C, D square from the previous part of the problem, and you can kind of see now how this square might be sitting on these stream functions, but it starts to get dragged and stretched, but not turned in this case. Not turned or distorted, just stretched or translated and stretched. And because it's incompressible, remember the same area in this rectangle area is the same as this square area in here. So the flow direction we do just like we did before when we were talking about streamlines. Stream functions and streamlines are pretty similar. In this case, we just look for where in the first quadrant, which is where we're worried about right now, x is greater than 0 and y is greater than 0, obviously, for the stream function. Therefore, ax is always going to be greater than 0, and negative ay is always going to be less than 0. So all these lines will have the arrows going down and to the right, as shown. These are just some values that I plugged in to get the other stream functions for psi2 and psi3. So remember one of the neat things about a stream function is that if you subtract one from the next one over, or even two over, you can get the flow that's happening between those streamlines. So for example, the flow Q between 1 and 2 is the stream value function for 2 minus 1, and that's 1 minus 0, or 1 meter squared per second. It's in a two-dimensional map, so it's not truly three-dimensional. So it's one way to think of it is 1 cubic meter per second per meter into the page. So if you thought of this thing as going into the page, you could go several meters and there'd be this deeper water moving in the same pattern that we've cut through here. Similarly, Q23 would also be 1. So the difference between each one of these is 1. But if we skipped over 1, we'd see the difference between Q3 and psi3 and psi1 is 2 minus 0, or 2 cubic meters per second per meter. So these are the flows happening between the lines. So that's one of the neat things about these stream functions, is that you can actually get a quantitative flow between them just by taking the values of those functions. So hopefully that puts together several concepts. In part 1, we saw the kinematics and how this shape is translated from A, B, C, D to A prime, B prime, C prime, D prime. We saw that it was not rotating. It was an irrotational system because those derivatives canceled out. And we saw that mass was conserved, which it should be for an incompressible fluid like this. And then we looked at streamlines and how we could sort of take the same idea and show it in terms of streamlines and show how this box would actually move on the streamlines. Finally, we saw that the flow could be determined by simply subtracting the values of streamlines to get the flow between the two streamlines. And that's it for this kinematics example.